Okay, dear students, the previous lecture just got interrupted abruptly because there is some problem with my phone. So let me continue where we had reached a certain point in our, just some elementary definitions in differential geometry, in which we have found that the alpha, which is a function of t. Now, alpha as a curve is defined as a function from an interval I to Rn. Now, I is an interval in R. It could be the whole of R, it could be minus infinity, infinity, it could be a closed interval, it could be a semi-closed, semi-open, open interval, just an interval. And Rn in our case, as I used to say, we would always treat it to be R2 or R3. That's the things we are going to mainly discuss in our course. Now, then we found that the alpha by dt was the vector dx by dt, dy by dt, dz by dt. Of course, I am assuming that alpha, my curve, is a function from an interval I to R3 defined by alpha at t as a vector is equal to x at t, y at t, z at t. So that was my curve, and from that I got this d alpha by dt, the tangent vector or the vector parallel to the tangent to my curve alpha at t. So in my 3 space, of course, since I'm assuming it to be inside R3, that's my codomain or range. So it lies inside R3. So this would be my x-axis. That is again a convention. We just take our axis in this fashion. And when I say draw x-axis like this, I mean like this. It's coming out of the page. Okay, so we usually denote it by alpha dot t. That's the notation used by Newton, and we continue with that. So this would be our dx by dt, dy by dt, dz by dt. Okay, now another thing that I want to, now we can also look at this curve as a path traced by a moving point. The point is moving, which is tracing a path, right? Then alpha dot t would be exactly the velocity of that point which is moving along this curve, which has been parameterized by my equation alpha t is equal to x at t, y at t, z at t. And at a certain point I would have alpha dot t, which would be basically the velocity of that point which is moving along a curve at a certain speed, which would be of course determined by x at t, y at t, z at t, right, which would depend upon my parameterization. Okay, because a curve can have more than one parameterization, and that would change its speed. For example, take the simplest of my curves. Take the unit circle. Unit circle is a curve. Okay, unit circle, by this I mean the Cartesian equation of this would be x square plus y square is equal to 1. It is a circle with center at origin inside R2, of course. We are living inside a two-dimensional space, our curve, and its Cartesian equation is x square plus y square is equal to 1. So one of its parameterization would be, of course, alpha at t of this parameterization would be, of course, I can take x to be cos of t, y to be sine of t. Now when t is 0, and of course I can have my interval t belongs to my domain as 0 to pi, right? So when t is 0, I would be somewhere here, because if t is 0, my point on the curve would be cos of 0, sine of 0. So that would be basically 1, 0. 1, 0 would be exactly the point here. So I am starting here, and if as t becomes pi by 2, I would have cos of pi by 2, and I would reach here. That is 0, 0, 1, right? Okay, similarly, when I did 2 pi, I would get back to this point. So I would have traversed all the points in that curve, right? But I could have also parameterized this curve. This could have been also parameterized at, let me call it alpha tilde, as cos of 2t, sine of 2t. Again, it is satisfied by everything here, right? Now when I move along this curve, when I am at t equal to 0, of course I would be here, right? But when t becomes pi by 4, I would be here. Now time has, if I see myself as a particle, as if a particle is moving along this curve, when the particle is here, when t is equal to 0, I get this point. So the particle is here at this point. T is equal to 0, I will again get cos 0 sine 0. That's 1 0 then at this point. But when t is pi by 2, right, or pi by 4, I would get if I draw another circle. Okay, now suppose that this is the same circle, same equation, but a different parameterization, cos of 2t sine of 2t. What would happen? So when t is 0, I would be here, but when t is pi by 4, now here it was t, when t is pi by 2, I am here. When t is pi by 4, I would reach this point, because this would be cos of 2 into pi by 4, that is cos of pi by 2. So this would be 0.01 when t is equal to pi by 4. And when t is equal to pi by 2, I would have already reached here. So if the curve can be thought of as a particle moving along a path in R2 along this circle, then this particle is moving twice as fast as this particle. Although the circle is same, the set of points is same, the geometric property is the same, just by a different parameterization, what happens that firstly it gives a direction. I should have said that earlier. This parameterization gives a direction to an orientation to my curve, and I am moving in this way. Although that's insignificant when it comes to the geometric properties. Also, it is slower than this parameterization. This is twice as fast, of course, in the same direction, right? But it doesn't change the geometric properties. But parameterization does change the speed of the curve. So parameterization basically doesn't change the properties of the given curve. Furthermore, I could also parameterize it as, if you see, it would be, if I write it as sine of t cos of t. Now what would happen then? Now when t is equal to 0, right, it would be 0 1, so I would be at this point, right? And when t is equal to pi by 2, I would be at this point, right? So then I would have a different orientation to the curve. Of course the curve would be again the same, but a different parameterization. Parameterization means an equation and parameters for x and y which would satisfy this property. So what I'm trying to say, the reparameterization, or changing the equations without changing the condition on the points on the curve, would only result either in the change of direction of my curve, which is a material for geometric purposes. It doesn't affect it. The geometric properties of the circle would be same whatever my parameterization, or it would change the speed of the curve. Okay, now let's move ahead and come to some definition of we come to definition of arc length. And we want to measure if this is now my general curve, I want to measure, so this is alpha t, of course inside my three-dimensional space. That's what we are going to deal with mainly. It is a curve in space, and I want to measure, of course, alpha. I want to measure the length. I want to find the length from a fixed point to some other point, right? Now let me recall for that the length, the notion of the length of a vector. Now if v is a vector in n dimensions, it has got n components, right? Then we know that if u is another vector with n components in the same space in n dimensions, of course this belongs to Rn, this belongs to Rn, then we know that dot product of u dot v is u1 v1 plus u2 v2 plus so on and so forth plus un vn, right? And length of any vector v is basically square root of u1 square plus u2 square, in this case, sorry, v1 v2 square, so on and so forth. And the connection between the length and the dot product of vectors is basically v dot v would always be equal to the length of v square. This is the length of the vector. We are going to define it by this symbol. Okay, now I want to find the length of a part of a curve, right, from a fixed point which I can denote by alpha t naught to some other point alpha t, right? What we do, we first observe that if the points were very close, then suppose I have a point here alpha t, I have a neighboring point alpha t plus del t, right? Two vectors, position vectors of these 2 points on the curve in R3. Let it be alpha t and alpha t plus del t. Then if they are very close, then the length of the arc would be, if I take delta t to be very small, it would be, because the smaller it gets, it becomes approximately equal to the arc length. That means the length of this vector, which would be alpha t plus del t minus alpha t, this length would be approximately equal to the length of this vector. That means this thing, norm of this thing, would be approximately equal to the arc length in case delta t is very small. But in case delta t is very small, alpha of t plus del t minus alpha of t would be approximately d alpha by dt into delta t, because you know that when delta t approaches 0, we will get the equality, right? So I can think of the arc length for an infinitely small, very small piece of the curve to be length of alpha dot t into delta t, right? Of course, alpha dot t is our notation for d alpha by dt. Okay? Now if I want to find, I just sum these up, and summing up is the same as integration. Then we would get, as delta t becomes very small, our definition for arc length should be s of t equal to t naught to t mod of alpha dot t dt. So that would be our definition of arc length from an arbitrary point alpha at t naught. So this would be the arc length from alpha at t naught to alpha at t. And of course, if we differentiate by fundamental theorem of calculus, I will get ds by dt is nothing but alpha dot of t. So I have arc length differentiated with respect to time. Arc length, if I think again, if I think of curve as a particle tracing a path in R3, and then arc length, the distance it covers, differentiated with respect to time, should be the speed. And speed is nothing but the magnitude of the velocity. So our definition is very consistent with what we already know. So this would be our of course you would look also at your notes that I have provided you. Okay, so another thing is something that obvious, at is t naught is equal to 0, because this integral from t naught to t naught would be 0, and of course if t naught lies ahead of t, if t naught t is bigger than t naught, this would be positive, and it again would give a sign to the length, because primarily because when we parameterize a curve, it automatically gives it a direction, as I showed you in the case of circle. If I change the parameterization, it could change the orientation of the curve, or the direction of the path traced by a point on that curve, because a particle can go on this curve along this direction and along this direction without changing the curve, actually the geometric properties of the curve. Okay, now we come to another definition. Now, since what we is clear from what we have done so far, the speed of the curve does not change the geometric properties of the curve, because it would again trace the same set of points in our space Rn or R3. So we define what we call a unit speed curve. The unit speed curve would be 1 in which norm of alpha dot t is equal to 1 for all t. Whatever the values of the parameter alpha dot t, that means the speed of the curve is 1. We call it unit speed curve, obviously enough. Now before moving ahead, we just want to do a small theorem which says that if you have a unit vector, a vector of length 1, like in the case of a unit speed curve, then if I have a, let me denote it by, you just look at the notes, then it would be clear. If you have a vector, let's call it n at t, which is a unit vector, right? It means that n of t is equal to 0. Sorry, n of t is equal to 1. If I have a unit vector, then if I differentiate it and get n dot t, I am differentiating n with respect to t. Its magnitude is 1, but it is not a constant vector. It may change its direction, because vector has got two things. It can change. It can either change in magnitude or change in direction. But we are seeing that it has a fixed magnitude, but it's not a constant because it can still change its direction. If that is the case, if you have a fixed magnitude of a vector, then n dot t dot nt, if I take the dot product of this vector, which is of fixed magnitude, with its derivative, it would be 0, right? Which would imply either n dot t itself is 0, because this cannot be 0 because it has got magnitude 1, or n dot t is perpendicular to n of t. Again, it's very easy to prove and it's given in the notes. So what would that mean? If you have a unit speed curve, then I know that alpha dot t in magnitude is equal to 1 for all t. So applying this theorem, it implies that alpha double dot t, double dot I mean alpha double dot at t would be d by dt of alpha dot t. It is the derivative of the velocity. So applying, thinking of alpha dot t as nt, I should get alpha double dot t dotted with dot product with alpha dot t should be equal to 0. That means that's an important thing that we get. That means alpha double dot t should be either 0, alpha double dot t is equal to 0, or alpha double dot t is perpendicular to alpha dot t. And if I think in terms of if I think of the curve in terms of a particle moving along a path in R3, if alpha dot t becomes then the velocity of that particle, and alpha double dot t would be the acceleration. So it is saying that if a particle is such that its velocity is fixed, then the acceleration would be perpendicular to the velocity, right? Acceleration would be perpendicular to the velocity in case either the acceleration would be 0, in which case it would be a straight line, right? Because if a body is not accelerated, it tends to move in a straight line. But if it is of magnitude 1 and changes only its direction, then its acceleration must be perpendicular to its velocity. The best example could be the unit circle, the particle moving on a unit circle. Its magnitude is of course 1, because if it is alpha t would be cos t, one of the parameterizations that we did, right? Then alpha dot t is of magnitude 1 because it is minus sine t cos t, and if you take the magnitude of this vector, it is 1, right? And velocity is in this direction, it's of magnitude 1 again. And where does the acceleration is in this direction? So acceleration is alpha double dot t. Since its magnitude is 1, it would be again of magnitude 1. It would be minus cos t minus sine t, and it would be in this direction. Obviously, if the particle is moving in this direction, there is some what we call centripetal acceleration. So what I'm trying to say, from this we get that if we have a unit speed curve, then its acceleration or its double derivative would be perpendicular to its first derivative, that is alpha dot t. Okay, another thing is about this reparameterizations of the curve. So we define reparameterization of the curve. We just reparameterized a certain curve, didn't we? We had this parameterization for a unit curve, for a unit circle. What was that? I had one parameterization alpha at t, that was this first one, cos t sin t. I could also reparameterize it to be alpha at t is equal to cos 2t sin 2t, isn't it? And I could also parameterize the same curve as minus, hey, let me call it sin t cos t. These are three parameterizations. There could be infinitely many actually of the unit circle. A circle with center 0, I draw it roughly. Okay, of center 0 with center origin and radius 1. So now we define what do we mean in a rigorous terms. What would be a reparameter? What would a reparameterization mean? So by that we mean, if we have two parameterizations of the same curve, we would only admit a certain type of reparameterization. And of course in the notes there are certain things that will clear that thing, but let me first give the definition. Alpha tilde, which is a map from an interval a tilde to b tilde to Rn, is considered is a reparameterization. Is a reparameterization of a parameterized curve. I already had parameterized it. Now what would be considered as a reparameterization of the same curve? Reparameterization of the parameterized curve alpha from the interval AB to Rn if there exists a smooth bijective map. Bijective means which is 1, 1 and on 2. Bijective map between the domains of the two parameterizations of the curve. Phi from A tilde B tilde to AB. Now remember that when I say smooth, by that I mean differential. Its derivative exists, right? Such that phi inverse, which would be a map because it's a bijective map, I will have the inverse to इसका inverse जो होगा, that would be from AB to A tilde B tilde, is also smooth. That means I would consider one parameterization of curve to be the reparameterization of the same curve if there exists a function which is bijective 1, 1 onto and is differentiable, and its inverse is also differentiable, such that alpha tilde at t tilde is equal to alpha at phi of t. Phi of t tilde, because phi is a map from another parameter. This is the parameter. We denote this parameter inside this interval to be t tilde and here to be t. Okay, so basically it has to be a composition of that reparameterization map with the first parameterization curve, the curve. But you just read it properly, there is no problem. It's not that complicated. It's very difficult. Which also implies that I could have also written the same thing as alpha tilde of phi inverse of t is equal to alpha at t. It is one and the same thing. Okay, now if I apply, what was the reparameterization map here? Now if I take my alpha at t, as in my case of unit circle, that should make it clear. If I take my alpha of t to be cos of t sine of t, and alpha tilde to be another reparameterization, that was sine of t cos of t. Now what is the map that connects the domain of these two of course functions, these two parameterizations of the curve? Alpha, if I let me call it t tilde. Okay, I can, it is just that t tilde is nothing but t pi by 2 minus t. If you see that, this is a bijective map between the two domains. That would be from 0 to 2 pi, and what would be that? It would be from, yeah, domain is same basically. You just have to translate it by pi by 2. So what I'm trying to say is this: alpha t is clearly, if I take this to be, let me write it like this. So t tilde basically has to go to pi by 2 to t. That means my map phi has to be phi of t is equal to pi by 2 minus t, which is both ways bijective and differentiable both ways also. So 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 reparameterization would induce a reparameterization map which would be bijective and smooth, and its inverse would also be smooth. By that I mean differentiable. Now another thing is a point of a curve. Another definition: a point of a curve is said to be regular if alpha dot t is not equal to 0. If its velocity vector or its first derivative is not 0, we call it a regular point. Otherwise we call it a singular point. And if all the points of the curve are regular, we call it a regular curve. For example, as we already showed, that alpha t equal to sine t cos t, right? So it is a regular curve. Is a regular curve because all of its points are regular. Alpha t is equal to, इसका derivative होगा minus cos, नहीं, it will be cos of t minus sine of t, and of course they can never be both 0. So alpha dot t is not a 0 vector for any t. That means every point on this curve is regular. And if it is not regular, we call it a singular point in case the derivative vanishes. Okay, you just have a look at it properly. Okay, now any reparameterization of a regular curve would be regular. So there is a small result theorem: any reparameterization of a regular curve, reparameterization won't change a regular point to a singular point. A regular curve is regular. Now what I do, I will just leave it to you. It is very easy to prove and it is given in your notes, so you can easily do that. Okay, now there is another result. Now remember this: any reparameterization of a regular curve is regular. And then another lemma, and the basically, okay, let me stop there. It's already 28 minutes. Then it is difficult, becomes difficult to upload, so I stop it here.